Okay, then good morning, everyone. So today, sorry, today we want to continue with our communication chapter. And yesterday we stopped at message-oriented middleware. So we discussed sockets, and sockets are efficient, low level, but also not suitable for all transport layer protocols. As we have seen, this was tied to a few transport layer protocols like the TCP/IP protocol, and there it worked quite well. But in reality, there are many different and often complex interfaces or transport layer protocols with such interfaces, and they require special buffering or synchronization features. They don't all allow us to blindly write into a buffer, and they also always hand us the number of bytes that have successfully been written to that send buffer. And that's kind of something that we needed for sockets to make it work. Otherwise, there's little chance we can get our arbitrary large and complex objects or byte arrays across the network. And here are a few examples. Transport layer protocols have numerous interfaces. So many of them are very specific to certain certain technologies and hardware infrastructures that force also higher level protocols into their paradigm and their way of thinking. So there's no standardized interface above the transport layer protocol that all the applications can use. And this heterogeneity caused a lot of trouble in the past. Transport layer interfaces are sufficient but not convenient. Every communication involves a lot of redundant code, and transport layer buffering capabilities are limited. Usually fixed size buffers where flexible message queues are needed. That's exactly what we have seen yesterday. And this is something that developers in the past got around by implementing different solutions for it. And if you switched your infrastructure underneath, then they also had to change their communication protocols and communication strategies. And that's exactly what you want to avoid with this layering structure. That's why middleware systems have been developed to basically provide your application with a uniform interface such that you can actually exchange your transport layer protocols and their different APIs in a way that does not affect the application. So our focus today are middleware structures. So a special layer for distributed systems that provides a unified API, and many offer additional convenience features with respect to buffering, communication protocols, and failure handling, and so on. So we talked about the middleware structure already at several places. So this is a software that stretches across several nodes, and the purpose is that it eases the development of our applications by providing these unified APIs. Right. There are a few very popular middleware infrastructure. There are a lot of them, but I want to talk about a few very popular ones. And in this section, I want to talk about those that are message oriented. So these do not change our messaging paradigm. They still rely on getting objects, serializing these objects, and then sending them around. What all of them do is that they can take arbitrary large objects and then send them around, so that we don't need to bother about the splitting of these objects into smaller pieces so that they can be streamed over, or in a loop, pushing more and more bytes to our buffers, such that in the end they will eventually be sent over the network. That's what they do, and they also standardize the interfaces. We already talked about actor programming, and in actor programming, the transport layer protocols are just a configuration that you provide, but then we have the uniform API of building actors, formulating messages, and then just telling them to other actors. And if something changes under the hood, then we just don't need to care. But there is one even more popular message passing system or message passing middleware, which is MPI, the message passing interface. This is super popular in high performance computing, and that's also why we need to talk about it. Some distributed computing lecturers decide to do this also in their exercises. But well, this is even a little more complicated as actor programming, as you will see in a minute. But as I said, more efficient. Right. So what is message passing interface? So it's a specification for a family of transient message passing libraries. So there are different implementations of this specification, and you basically choose the one that fits your programming language. The most popular implementations are for C, C++, and Fortran. Of course, for the more efficient programming languages, because if you choose MPI, then your focus is probably on efficiency and and not on large system design. So, for instance, implementations are MVA, PI, CH, OpenMPI. OpenMPI is probably the most popular one, and also the one that is usually picked in distributed computing lectures for exercises. But Intel MPI is an implementation, IBM Spectrum MPI, and many more. So there are flavors of these implementations, often also designed for specific purposes or infrastructures like IBM server infrastructures. Most of these are also Linux-based. Because Linux is historically more robust and also better controllable than Windows systems. Here, because you are in a programming language that is compiled into binaries for a specific operating system, this really makes sense that they also use these features. It's the most popular middleware for high performance computing, so you will actually find it all over the place. But many of the application level protocols that we learned about in our ACA slides, they also apply to MPI. So if you develop systems, then something like master worker pattern and others, they also apply in a very similar way to MPI. Right, it's highly efficient. It supports various transport layer protocols. That's what we want from this middleware layer. We can change the transport layer protocol if that is necessary without changing our application. It's really made for these. So if a transport layer protocol has certain features, like the streaming feature in TCP, then MPI will make use of it. They really implemented all these transport layer protocols into the MPI libraries, so you can use them as efficient as possible. You can also exploit special hardware features. So if your hardware offers certain capabilities, your network infrastructure, for instance, it is sensitive to the layout of your network infrastructure. If you have a star topology and in your physical wiring, or if you have a ring topology, if all your computers are connected in a ring, then this is something that MPI can exploit in the computation and choose the most efficient strategy for sending around messages in this topology. So that makes it so efficient. And that's also something that ACA wouldn't be able to do. It's highly versatile, so it supports buffered and non-buffered communication, supports synchronous and asynchronous communication. We will see that MPI is essentially a huge library of different methods that let you send data around in the cluster. In ACA, the interface was pretty small. It was just telling messages and asynchronous communication. Here you have the full bandwidth of everything that you want. So this makes the API quite complex. Many of them have more than 440 low-level message passing functions. And every time that you send a message, or that you want to send a message around in the cluster, you have to choose and think about which of the functions would be the most efficient one. So that provides you with a lot of performance, but also yeah, makes your algorithm design and computation, or no, not computation, but the algorithm design more complex, because with every send you have to choose the method that yeah, should be used for sending it. All right. So there are some core concepts. So it's message aware. Message aware means that MPI manages messages of variable length as entities for transmission, which means that it sends and receives messages as they are defined by the application. That's very similar to Akka. You have your messages, you serialize them, send them away, and done. Then we have abstract process identifiers. So we don't have actors. So we need something else to identify processes in your application to send data to them. So MPI associates every process with an identifier and then translates these identifiers transparently into process addresses. So as a programmer, you also don't need to bother with all the IPs and ports, but you have to work with identifiers. That's a little bit more difficult than working with actor references, but that's kind of their way. So they don't change the programming paradigm from object-oriented programming or imperative programming in general to actor programming, but therefore they need yeah, to work with identifiers in order to address processes. MPI categorizes communicating processes in groups, which all receive abstract identifiers. So that's also a feature, if you want, from MPI, so that you can work with entire groups of processes and that helps you in certain messaging functions, as we will see later. So then a pair of a group ID and a process ID then uniquely identifies a source or destination if you want to send or receive something. Right, and then we have transient communication. So before I told you we have, if we go back, we have both buffered and non-buffered communication. We have both synchronous and asynchronous communication, but still with respect to the third feature, it's always transient. So there is no middleware infrastructure that persists messages and basically buffers your messages so that sender and receiver are decoupled and don't need to be active at the same time. So messages are still sent directly, but don't know, but it's just it is transient. There's no buffering inside the middleware, no third parties. If you want to send something, then processes need to be reachable when you call the sending functions. All right, and that's so the last point. The transient part is the part that we will tackle with a different message-oriented middleware later on, but here still transient. And this is a small example of an MPI session. For MPI, we have to switch to C++ or Fortran or any other low-level language. And so here we have an example in that should be C++, I guess. First of all, we import some header files that we need for MPI to work. Then we enter our application. Then we define some variables that we will need throughout our computation. So that's in the beginning. We also have a status flag for our send and receive commands so that we can always check did it what was the status of my send? Did it work? Did it fail? So this is always provided to us. Then we have to initialize MPI, so the environment. In this case, we need the take the program arguments to initialize our MPI environment. We set the communication. Or I guess I have also some pop-ups here. We specify some other communication parameters like the communication site, So in MPI terms, we have to assign process IDs to all our processes, and this has to happen at some point in time. And this is actually the point where this happens. So these in the MPI COM world, we can fetch all known processes of the cluster. So they are already known, and this is quite similar to our clustering feature in Akka. So these are all known processes then in the cluster that have been connected by MPI. And from that, we can fetch also the rank. The rank is the process ID of the process that we are at the moment. So if we start a new application, we also need to figure out what our own process ID, what our own role in the system is. And MPI will automatically assign these process IDs, and here we figure out what our own is and store it in rank. And now that we have our own process ID, we can check what we need to do. It's very similar to the roles that we assign to actor systems. So now this system here knows what it is, what it should do. And here it decides, well, okay, if I'm rank 0, then I have to take this role here. If my rank is 1, then I execute this part of the code. So well, let's say here I'm a server, there I'm a client. Right. So if I am, let's say, the server, then I want to send something to the client. If I'm the client, then the destination is my server. And well, it's still working with send and receive operations. And MPI, we have to explicitly, very similar to the socket-based setup, we have to explicitly send stuff to other processes, and they need to be prepared to receive whatever is sent. Right. So we basically here use the MPI send function. And we want to send a certain out message. Let me see if this also is something. Our out message is initialized here. So our out message is just the character X that we want to send. We want to send it to. We are sending this. And there the difficulty starts. So with a few parameters, the destination should be the other rank that is specified here. We specify what type of message this is. So it's just a character that we want to send. We want to use our MPI COM world for sending the message. So this is here we provide the context of the send operation. And there are a few tags that we can specify to modify and configure our send. And I don't even know what the one here means. And that's kind of the trick here in MPI. You always need to check a couple of parameters for the different sending and receiving functions that MPI offers. And that's kind of a disadvantage in MPI and an advantage in something like Akka, where it's more naturally explaining. Okay, but this is a send call with lots of parameters, of course, our message and to which process ID we want to send it. Once the send completes, we get our status code. In this example here, we don't check the status code, but instead we directly attempt to receive a response message that we want to store in the in message variable. We expect another char and also from our world, right. And the opposite here, if we are rank 0, then we first expect that someone sends data to us. So we first fetch a message, and then we respond to that message and send some out message back. Right. And in the end, we call MPI finalize to end the application. All right. As you can see, this is a little bit more complex, and even me, hard to remember what all the parameters mean. And it gets even harder because, as I said, There are many of these send and receive operations, and some MPI implementations, more than 440, that all come with their specific interfaces and their send and receive specific configuration parameters. Right, but by providing all these information explicitly, MPI is actually able to optimize for the specified send operations and make it as fast as possible. Right. As you can see, this is also one of the book slides, so you don't have to be able to program MPI in the exam, but it should just give you an impression of how else then in akka terms you can build your application. Right, and now to the synchronization, because MPI actually allows you to choose the synchronization that you want for a specific call. If you, as in the example before, just call the MPI send, then this is kind of a semi-asynchronous send. It makes sure that the other side, the other process, has received the data, so it has been copied out of your local buffer into the buffer of the receiving side. You cannot be sure yet that the message was actually received by the receiving process, but it has been sent and can be modified afterwards. But a few modifications to the send call. So iSend is fully asynchronous. bSend at least waits until it has been handed over to the local buffer of your MPI middleware. MPI send is somewhere here. Send is somewhere here in between, so it's in the process of being sent. And we have also the MPI send receive, which actually sends some data, and it directly afterwards expects that some response is received, so that actually the receiver has received the message, has calculated it, and has responded with a certain other message. So this would be the fully synchronous send, the fully blocking send. Right, and this is only for the send and only a couple of send options. You have the same also for the receive, and then there are some more functions that we will discuss in a bit. So different MPI library implementations may offer only a subset of these send operations. So the standardized interface is quite large, but you always have to check in your MPI library if a certain function is implemented or not. And even the semantics may sometimes differ a little bit. So there we have to pay attention. Right. And because we have all these different flavors of blocking, non-blocking, synchronous, and asynchronous terms, only blocking and synchronous are not even sufficient, or only the blocking synchronous and non-blocking asynchronous are not sufficient. So MPI actually specifies its very own interpretation of blocking and synchronous. So first of all, it distinguishes between blocking and non-blocking calls. Non-blocking means that the send call returns immediately and the message in the send buffer should not be modified. So this call here would be non-blocking in MPI terms. But if we have a blocking call, then this blocking call can also be more fine-grained, be distinguished. So first of all, blocking says that the send call returns if the data was sent in some way. So the message in the send buffer can safely be modified. But this can also be synchronous or asynchronous. So blocking synchronous means that the receiving side has actually acknowledged having received the data. So if we go back, then this here would be blocking and synchronous because the side has acknowledged it has received the data. So the send was successful. Even if this process here dies, the data has still successfully been sent. But we also have blocking asynchronous, and then the system buffer acknowledged having received the data. But the system buffer, so the system buffer copied the data and will make sure that it gets sent, but it's still likely in the same process. So it's somewhere in here. Oh no, this would be non-blocking where it directly returns. Here we at least copy it to the own system buffer. So this would be blocking asynchronous, blocking asynchronous, and then we have blocking synchronous in the MPI send operation. So that's kind of their interpretation. It's just something that you have to get used to if you browse the repository, the documentation. They decouple these two terms. In many other documentations, blocking actually also means synchronous and non-blocking means asynchronous, but here that's their specific terminology. Also in this terminology, RabbitMQ, Kafka, Akka, and other JVM-based message broker are non-blocking asynchronous. So the message should not be modified and it arrived in the message broker. But yeah, usually it is treated synonymously, blocking synchronous and non-blocking asynchronous, but here we split the blocking term with the synchronous term. All right, now let's have a more concrete example on how these messaging procedures work so that we can see that everything is actually represented in the library. So first of all, we have these blocking, synchronous, and non-buffered send processes. We take the message from the representation in the application and copy it directly into the other application's address space. So we don't use any buffer space in MPI itself, but copy the data directly. And that's actually something that we can do with a send operation and would be the most efficient, probably, but also most risky one. So if something fails in the sending process, the application is responsible for it. We can also send the message directly to the system buffer on the receiving side. So the application on the other side doesn't have to be directly involved. We can first copy data over here, and then we bring the data into the address space of, we copy the data gradually from the system buffer to the application. Performance implications, well, because there is already system buffer, maybe this send can even start earlier, sending the message and doesn't have to wait for something like a rendezvous protocol to be executed in order to allocate the memory here. So maybe the sending starts earlier, but there is one copy operation more that we need. We can also use the system buffer locally. So we copy the data over locally first, then MPI will move it over to the receive system buffer and then copy it to the application. Or third, we can have a non-blocking asynchronous buffered communication where the message is gradually fetched from application code. So the application said, please send this message here, and it asynchronously directly continues working. So it should not change the message because the message is still in the process of being copied to our system buffer, but the application can already continue. And when the message has been copied over, then it is sent over to the, not even that. It can be, if you use TCP under the hood, that the message is copied in the send buffer, while at the same time it's also streamed over to the system buffer on the other side. And the system buffer then can construct the object in the application. Well, maybe my assessment of speed is not even accurate. So it might be that this here is even faster because we can fully stream the stuff over. So I guess performance considerations really depend on how the concrete MPI implementation implements this behavior. These are the 4 different ways a send can work and can use or not use the buffers that are in MPI. Okay, so yeah, and like I said, with every send operation, you have to choose which send you would like to have executed, and then the according strategy is done. And for our application, of course, what concerns us is, can we alter the message in our code? Has it already been handed over, or should the message be treated as immutable because we don't know in which state it is at the moment? Right, and can we, or is this a blocking call, or does it continue right away? So I guess these are the two most important considerations. Right, and also, yeah, okay, for security, if this is a blocking synchronous call where we actually wait for the receiving side to acknowledge the entire message, that has the implication, well, if we make sure that this is the case, then we know the message has been sent and nothing bad has happened. If we choose one of the non-blocking asynchronous strategies, then we might need to wait, like in ACA terms, for an acknowledgement to be actually safe, and know that a message has been transferred and operated. Okay, so like I said, we have to choose our poison when we choose the send operation in MPI terms. But there are, so these few functions, so like 4 or 5, 6 flavors of direct sends and direct receives do not count up to 440 different functions. So there are a few MPI send functions that are quite unique and that also make MPI so strong. So yeah, very similar to ActiveMQ or other messaging libraries. Also, MPI offers a few functions that come in very handy because we might use them in our application often and would otherwise need to implement something around the send operations. We can distinguish between point-to-point communication, where one thread in a process sends a message to another thread in a process, and this has all the synchronous, asynchronous, blocking, non-blocking features, and the collective operations, collective send operations, and they have broadcasting and broadcasting and broadcasting and how was it called? Scheduling features, so that you can basically schedule multiple messages on different nodes. So if you just want a scheduler, then this is also possible as a collective communication function. Right. So here the setup is that one process or thread wants to communicate to multiple others, or multiple processes need to communicate stuff to one. Here we see examples of it. So first of all, broadcasting is when like we have seen before, when one thread wants to send something to many other threads. So the same message is sent to all of them. And in MPI, we have something very unique, and that's the opposite of it. It could also be that many processes have to send some result back to one process. These two here often work in tandem. So one process often wants to broadcast a message to many others. And then when all these have finished, you want to collect all the results and send them back to this sending process. And that's the MPI gather operation. That's kind of the inverse. And then another popular one is the MPI all gather. This is when many computers or many threads want to share all their information with each other. So yeah, like a machine learning setup. So this is often used in machine learning when you want to synchronize your different locally trained models with all the other models in the cluster. Yeah, federated learning is something that you can implement with an all gather. So all worker or all threads train a local model on their local data instances, and then they want to exchange all their weights so that all models update each other. And well, then you just call a MPI all-gather function with the weights, with the model weights that you trained, and then every model, every process will get all the weights of all the other processes, and can update the local model and then continue the training. And you hope that after a while, all models converge to the same global model. So that's MPI all-gather. And these functions, these specialized functions, they make the libraries big. They also come in different synchronous and asynchronous implementations, and allow you to communicate data in your cluster more efficiently. If you were to build this in Akka, then you need to build broadcasting, gathering, and all gathering as your own protocol, and you have to decide how messages need to be passed around, because there is only point-to-point communication in Akka. And here we have these collective communication functions, so that you can do this more efficiently. Here on the right, you can see how it works. If you are in a broadcast situation, then there is one process, the one with process ID 0 in this case. And this process has some data and wants to send the data to all other processes. And if this guy here calls a broadcast, and after the broadcast, all the other nodes have received his data here, and you broadcasted the data. In the MPI gather, you have this is not gather, this is scatter and gather. So first of all, in the scatter case, there's one node, and this one, in this case again, the one with process ID 0, and that node has a lot of different data items. If you call the scatter is what I just wanted to explain with the scheduling. You want to send all these work items to your workers in the cluster. In MPI terms, this is a scatter operation. So there's after the scatter, every item is shared to a different process, and only one process. So after the scatter operation, you basically partitioned your data to the cluster. And if you want to do the reverse, then this is a gather operation. So if all of the different processes call the participate in the gather operation, so process ID 0 calls gather to get all the data from the cluster and fetch the results back. Then all these here gather their current states to a specific process ID. And well, then you collected all the results. Right, so you can do either a broadcast, then they compute everything, and then you call a gather to get the results, or you do a scatter, and then they compute on different data items, and then you gather the results, and that's also possible. So these are very typical back and forth operations in MPI. And for the MPI all-gather, you want that every process shares its information with all the other processes. So here, every process has some different results, some different machine learning model that it trained locally. And then you call the all-gather so that not only one process gets all the different results, but every process gets the results from all the others. Right. So very popular functions, and the trick here is that MPI actually optimizes these operations, and even in a way that the optimization fits the underlying transport layer protocol. So if you have a certain topology in your network, then gather might work differently from a different topology. And that's what we will discuss next. So here's some further reading. As I said, there are more than like broadcast, gather, all gather, and scatter, which is also here. There are more, and yeah, check out the library if you want to figure out what you can do else with MPI. But these should be sufficient in order to explain a few general concepts for the optimization. So first of all, if MPI wants to optimize for one of these calls, then the first thing that it introduces is the concept of a barrier. So a barrier is a collective operation that is executed prior to larger collective operations in order to synchronize their execution. So if you call an all-gather operation, then you let all of your processes, first of all, run into one barrier. So they wait until all the others are ready. There's some synchronization. So this guy here is still in processing, so they cannot continue. And once they are all in front of the barrier, then they continue and can execute the next collective operation more efficiently because they are all in the same state. And for the execution, so the step that comes after, you want to do something that fits your underlying network structure. So let's say you want to broadcast something, and your MPI setup knows that it is working on some parallel network architecture. So something where you can send messages to all of your nodes in parallel. Then it will exploit this and actually send data to all target processes in parallel. However, if your network actually does not support such a parallel send operation, for instance, because you are in a ring or because there is one central switch one central hub in the network, and there's a large shouting chamber for all of your processes. In that case, it would maybe make sense to choose a different strategy. For instance, the sequential send. So you could use process ID 0 and send the message to 1 first, and then 0 and 1 have the message, and 0 can then send it to process ID 2, and in parallel 1 can send it to process ID 3. Then 0, 2, 1, and 3 have the data and send it in parallel to 4, 6, 5, and 7. This only works if you organize your communication so that you don't send messages redundantly and have a clear structure who needs to send which, who needs to send the message to which other node next. Of course, this here requires a few barriers and executes everything in waves, but it's the most efficient send strategy that you can use if you can send data only to one target at a time. Of course, you could also say, okay, 0 sends it to 1. Once this has been done, then 0 sends it to 2, then 0 sends it to 3. But that takes way longer than if you would exploit the fact that always two pairs of processes can communicate in parallel in a certain network infrastructure. And I guess I don't have a slide now. Don't have a slide. There are other strategies for these altogether. If I go back here, this altogether, for instance, is also something that we can very nicely optimize because we know, well, sending stuff around is quite expensive. So we want to minimize communication costs. And a very effective strategy for altogether is actually by sending the information in a ring. So it's called the ring altogether, and you would start with one node. I don't have a ring here. You would start with one process, and that process opens a token, attaches its information to the token, and sends it in a ring to its next neighbor. That neighbor takes the information out from the token and or copies the token and adds its own information to the token. Then the token moves to the next one with now the results of the first two. So the third one gets the results of the first two and adds its own result to the token. So the token has to move twice in the cluster. In the first round, it always grows. In the second round, it starts shrinking. And this is the most efficient way to communicate your results to all the nodes in the cluster, especially if you can only send one piece of information at a time. Or you even have a ring topology physically in a cluster and just send the token around. So these are specific strategies like ring sending or broadcasting in parallel, or using a hierarchy of nodes and sending them also in parallel as much as possible. Right. Good news is you don't have to implement this yourself if you use MPI. If you use something else like Akka, then this is exactly what you would need to implement if you broadcast something and want this something to be broadcasted efficiently. But in general, this is where the performance of MPI comes from, by these internal optimization for certain send operations. Okay, all right. Let me quickly check if there are there any questions for MPI? No. Okay. In that case, we can continue. Just keep in mind that there is something like MPI with a very strong and large library with different flavors of send operations, a lot of freedom in the choice of how stuff gets sent around in the cluster. And well, your basically technology of choice if you want to build a high performance distributed application. But be aware that this is in many ways also more difficult to write because of the increased complexity of the more choices that you get. And of course, MPI is used only for sending messages remotely. If you also want your applications to be parallel, then you have to mix MPI with some threading strategy, so that you do parallel computing and distributed computing at the same time. While in actor programming, you can do both in the same way, and the library or the actor system will automatically recognize if something needs to be executed in parallel on one machine, or if you have to move computation to a different node. So actor programming, here just as a small recap, it's for transient message passing, also like MPI. And the focus here is not so much on high performance, otherwise you would have probably chosen C, C++, or a lower level programming language anyways. This is more about reactivity, so algorithm design and maintainability, fault tolerance. If you build something larger, more complex, then you sometimes gain more performance from a well-maintainable architecture than from a potentially more efficient message passing library. And also fault tolerant for MPI, we have these status codes that we get as a result from every send operation that we can check. And we also have fully blocking synchronous calls that we can use to make sure that a message is actually transferred. But there are not many features that help you when nodes or processes, threads die, if there are other problems in your algorithm. Then you basically have to do this all yourself. Also, the actor model helped us to build more robust applications, because some faults like deadlocks are just easier to avoid, and they still can happen, but then you should see them more easily in your protocols. And that might be just different in MPI. In MPI, this can very easily be constructed if something has been sent and you actually would assume that the other side now calls a receive, but instead, the other way around, two sides both assume that something will be sent to them next. So they both go into a receive function call, and then they wait blockingly for something to be sent to them, but actually they wait for each other, so they are in a deadlock. And well, these situations, if you have to call sends and receives explicitly, are just way easier, or also by accident more likely to occur than actor programming. And that's why we call actor programming more fault tolerant and maintainable. Okay, but here just a recap of what we have already talked about. So the actor model is a result of the reactive manifesto, responsiveness, resilience, elasticity, and messaging for building distributed applications. They basically have figured out that building distributed applications is very prone to errors, and something else needs to be done. And then the reactive manifesto was put in place. Actor programming is one, probably the most popular result of the active manifesto. And we formulate now everything in our applications, not everything, but the core concepts in our application as actors. There are still objects that we can use for data holding objects or for designing our libraries, but the main modules or entities in our application should be actors. And in particular, there should be no parallelization within an actor. If we want to have something happen in parallel, then these should happen in different actors. Also, immutable state of messages and private state, these are all features that make our life easier in the long run as soon as we have gotten used to it. So here also just a summary, private state and behavior, message queue, we send messages, smallest entity of parallelization. Everything is reactive. So these guys here are passive unless they receive a message. And this reactivity, this automatic activation once inputs are there, this relieves us from the burden of declaring receive functions explicitly like we did in MPI. So under the hood, of course, the actor system needs to do this, but we don't have to specify this actively. Right. Reactions can be sending an infinite amount of messages. Hi. Changing own state and behavior, and creating a finite number of new actors. Actor model principles, asynchronicity, encapsulation, distribution, parallelization, synchronization. We have already talked about them, so I don't repeat them here. There is still this step when an actor calls the tell function, then of course that actor needs to hand over the message to the middleware in order to continue. And this can be done in different ways. In akka, we said we want to be fully asynchronous. And if we do this handover via shared memory, there is actually the option also to do this via mutex and lock on that mutex so you can do the handover. And this is something that I just want to add, we can actually do this in a fully asynchronous way. So even this handover of a message to the middleware can be, if you want, done fully asynchronous, so that the entire path from actor to middleware to other middleware to another actor can be asynchronous. This is something that we can do with a blocking queue. If we want to just, if we want to hide the explicit locking, then we can do it in a blocking queue. But we can even do it with a non-blocking queue data structure that helps us to hand over data from an actor to the middleware in the same process without even blocking between actor and middleware. Right, so this is just something because in the past students were interested in how can we do the entire path asynchronous, and that's kind of the solution. So we need the non-blocking queue data structure. which is a queue based on an atomic compare and set operation. And it's technically an extension of the Triber stack data structure that has been published in 1986 by Mr. Triber. And here's how it would work. In the non-blocking queue, you have a linked list of nodes in the queue, and the list has a head and a tail. You keep a reference to the head and the tail that is initialized to null in the beginning. You queue up nodes. Every node in this queue stores the messages that you want to hand over to your middleware, and that is the generic type. So it can be of any messaging type that should be supported here. It could be just object, and then you send messages as objects. A node is double linked, so it has a next and a previous pointer. So basic programming, bachelor level programming task to build a double linked list. And there's a space too much. And yeah, we have a constructor that lets us put the message as the content of the node. For now working with this non-blocking queue, we need an add and a remove operation. So add is what our actor will call when it wants to send something. We just add it to the non-blocking queue. And this should be a non-blocking operation. So we need to work without logs here. And we need to remove if the middleware wants to remove a message to send it to the other side. Of course, this also works in the other way around. On the receiving side, the middleware would add received messages to the queue, and the actor would then remove it. So in both ways it works. Now to the magic. How can we add something to a double linked list without blocking? So in the operation, we take our arbitrary message that we want to send. Then we create a new node that encapsulates our message. We need a variable to store our current tail. The current tail now is the tail of our non-blocking data structure, which we store here. And then we say that our new node, the one that we want to insert, the previous one is the current tail. So we already link our new node to the tail of the list. And then we call an operation to our tail. So we take the tail of our list and compare it to the current tail. And if the tail is still the current tail, so the one that we linked to our new node, then we set our new node as the current tail. So this atomic operation is kind of how we solve the non-blocking part. In one operation, we check what the current tail is and quickly replace it with our new node and link it into the list. And we try to do this for as long as this here is actually the tail that we remembered. Because what could happen is we configure our new node that it links to the list, but before we can set our own node, some actor just added another tail node, and we should not replace the tail and remove it from the list by adding our own node. So this is why we compare the current tail with the tail that we assume to be there and quickly exchange it with a new tail. Right, and as soon as we could attach our new node to the list, we can now probably link also our node in the other direction. So, if the new node that we put into the list wasn't the only node that is in the list, so the previous would be null if this is the only item in the list. So if this is not null, if there is actually a previous node in our list, then we go to the previous node and send its next node also to the new node. So we probably link it in the other direction. But here, because we already put our new node to the tail of the list, there is some time that we have in order to also probably link it from the other side. And then we need another atomic operation. So we check if this head is 0, and if it is 0, then we quickly exchange it with our new node, and then we entered a message into the message queue without blocking even for the middleware. And for the remove, it looks very similar. Here we want to get an element out of the list. If the list is empty, then there is nothing that we need to fetch, so we return immediately. But if there is something to fetch, then we work with the current head and the next node. So we fetch the current head of the list, and we fetch the next node after the head. So because it's a queue, we want to fetch the head element. This is what we want to get out. And we store the next nodes that then should become the new head once we remove this head here from the list. So we first grab these two nodes, and then we do a quick compare and set operation. We check if the current head is still the head of the list, so that nothing has changed in between. If that's the case, then we quickly replace the current head with the next node, and that detaches the head from the list. And now we have the head that we can return, because it's not in the list anymore. Right. So this is how we quickly get new nodes into the queue and old nodes out without any blocking call. Right. And of course, if we go back, this is only if you not only want to detach or asynchronize actors from other actors, because that's done anyways. The actor just hands over the message to the middleware and continues. And then the middleware transmits the message, and at some point it arrives at the other side and an actor can receive it. But if you also want to make this communication here asynchronous, then you can do it with this non-blocking queue data structure. Okay, all right. So this was a quick recap on actor programming and how to make it fully all the way non-blocking. But now let's have a look at our third middleware, which is a message queuing, a larger message queuing system. So the main difference between something like MPI and actor programming was how deeply the communication impacts your algorithm architecture. For actor programming, this could overhaul your entire architecture if you also want to use it for programming. And it's also a performance decision. So MPI is faster than actor programming. But both have in common that they are transient systems. So all actors need to be active at the same time. All entities have to be active while they're communicating. That's what we sometimes want to avoid. And a message queuing, or some message queuing systems can actually do it, and also offer you the possibility to build a persisting message passing system. So their focus is usually on data-intensive communication. So both MPI and actor programming usually assume that most of the messages that you send around are rather small. We discussed this in length in the actor programming slides, where we discussed options to send more data, larger messages to other systems. But that's not their core capability. They're more about communicating smaller parts, smaller pieces of information, and just moving a lot of data around in the cluster is not their bread and butter. But that's different for many message queuing systems. They actually want to send a lot of data, and they're optimized to do this. And their persistent nature is often a way to deal with this. And also they are designed to build large-scale applications, more like also heterogeneous large-scale applications. From MPI and actor programming, we are always tied to the same programming language. And this is something that message queuing systems often decouple, so you can even connect applications or application parts that are written in different languages and different environments from each other. Okay, so also message queuing systems, first of all, are a family of systems. This is not one system with one implementation and one standardized interface like we have for MPI or for actor programming. here there are many different flavors of these message queuing systems. But in general, they are a message-oriented middleware. They are also still built on message passing constructs, and they provide various services for sometimes persistent asynchronous communication. So they deal with message queues. Message queues are intermediate term storage capacity maintained by the middleware. Of course, there are still the buffers on lower levels, but these message queuing systems now provide buffers in the middleware themselves, so where they can actually store multiple domain objects in one central data structure. They store the messages until they are delivered to, depending on how your delivery is defined, either all recipients or one recipient. And sometimes they are tied to sender and or receivers. If you work with the actor model, you are essentially also developing a system with a message queuing infrastructure. But message queuing systems can be more general than we have seen in the actor model. So in the actor model, they are tied to senders and receivers, but sometimes message queues can, or usually even message queues can be defined independently of concrete receivers and senders. So RabbitMQ, Kafka, also later on, they are message queues that are subscriber or polling based. So a message queue holds a logical, location-independent, system-wide unique identifier, so you can actually address your messages to certain message queues, and you can also read from certain message queues. Then we have some queue manager or queue management. In Akka, this was the actor system that manages all message queues and also the traffic between message queues. They are part of the message queuing system and handle queue life cycles and all message traffic. Even for Akka, also the queue manager manages the life cycle. So if an actor dies, then the message queue also dies with it, and the queue manager will remove the queue that was associated with an actor. Usually a queue manager is a separate process or library that is linked into the application. If you are working with a persistent message queuing system, then this is usually a separate process, so that even the entire communicating processes are independent of one another. But sometimes, and this is, for instance, the case in Akka, they are linked to our application, to the same processes. They live in the same processes as our main application and also manage their queues there. So here we already see how different message queuing systems are different. Sometimes they live within the same processes. Sometimes they create their own processes next to our application processes. Right, and a message queuing system requires a queue manager on every node. So even if the queues themselves do not live within the application context, a part of the queue manager needs to be active in every application because, well, they need to figure out how to find the message queues that we want to send or receive from. And they need to do the trafficking, the sending of data to the respective message queues. But we will see how this can work with different examples in a bit. So here, strictly speaking, if a queue manager or if all queue manager run within application processes, i.e. there is no separate queue manager process, then the message transfer requires both sender and receiver processes to run simultaneously, which is also the case in Akka. We cannot decouple the processes themselves. And that can, of course, be considered non-persistent. But if you consider the threads and not the processes as your communicating entities, then the threads can be decoupled from one another. Of course, one thread can write something into a local message queue and then vanish, and then on the other side, a thread can start and read something from a message queue on some other process. So the threads are decoupled, but the processes are not if you don't spend an extra process to your queue manager, just as a side note. Okay, yeah, some more constructs. Sender and receiver may not be active at the same time. They may be programmed in different languages even. In some message queuing systems, not in Akka, but in Kafka, for instance. Then we have messages. They need to be understood by the sender and receiver, which means that both need to be able to serialize and deserialize these messages. Sometimes if you have a language agnostic serialization format in between, then you can even let different languages talk to each other. We already talked about this. And they may not be understood by the message queuing system. So the message queuing system just takes the serialized versions of messages and passes them around. It's then up to the sender and receiver to deserialize the messages and pass them on. This is sometimes done so that the message queuing system is free from this, but some message queuing systems do understand the messages, which gives them the opportunity to even translate messages in the messaging process. But also more to that later on. And messages need to be properly addressed to a message queue, either directly to a message queue or by an entity that is tied to a message queue, like an actor. And messaging means that message transfers may take longer than with sockets, MPI, or RPC. In many of the message queuing systems, the design focus is more on throughput than on efficiency. So they use strategies like batching of messages. So while sockets, MPI, RPCs, they take a message and try to send it over immediately as fast as possible. And while a message queuing system might decide to first collect a few messages and then send an entire batch of messages at the same time. In this way, they can save some handshakes, they can compress these messages, and they can stream an entire batch of messages at the same time. Something like this is also used under the hood in Akka. So also Akka tries to, where possible, do a little bit of batching to optimize the sending procedures. But most message queuing systems do this even more extremely. They actually block messages and wait for more to come in order to send them all in a larger batch. The middleware guarantees that the message will eventually be delivered to the recipient. There is no guarantee on when or if the message is read. But once you hand over something to a message passing system, especially if this is a persisting message passing system, then the system can guarantee that the message will eventually be delivered. Right. And as soon as you have like a persistent one within its own process, then this message queuing system will often decide to do similar things than a distributed database. So oftentimes queues are replicated for reliability. So even if one process of the message queuing middleware dies, the data, so the message queues can still be recovered from a different host. So, well, these techniques also apply here then. The basic interface of a queuing system offers these functions like putting messages or appending them to a message queue, removing a message from a queue in a blocking way. So we wait until there is the next message and then we fetch it. We can pull a message, so we can test if there is a message and then fetch it, or if there's no message, then we have no result. And some of the message queuing systems also provide a notify option where we can install a handler, a callback function that is automatically triggered if something is written to the message queue. So this is the very basic general interface. Sometimes these operation names are different. and sometimes only a subset is provided. So some systems allow you only to poll, some only to get, and for some you actually have to specify a callback function. So there's only a put for senders and a notify for receivers, so they subscribe to a message with a callback function, and whenever something has been placed into the message queue, then they are notified and get the message automatically. Right. So this is just to be aware. This is kind of how message queuing systems want to be treated. So their task is message buffering in the first place. So this is what queuing is all about. They provide message queues, large message buffers for entire arbitrary complex message objects, they sometimes can also manage the subscribers or owners of these message queues. So yeah, in Akka terms, we talk about owners. An actor owns a message queue. In others, we have subscribers. And in some message queuing systems, there are neither subscribers nor owners. There are just message queues that processes can write and read from. Then they do message delivery. So they are answering poll requests or they do notifications of recipients. So either they wait for being polled or requested, or they are active message queues where they provide their messages actively to the recipients. Sometimes they ensure reliable message sends so that messages are not lost. So basically they send the message to the recipient and wait for an acknowledgement. If the acknowledgement doesn't come, they will reroute the message and send it to some other subscriber. Sometimes they enable synchronous message sends, so they allow senders to block on the message queue until a receiver has actually taken the message from the queue and then relieve the sender from it. But like I said, so these are all different flavors. We will talk about two specific message queuing systems later on that are very different and show you how these aspects can be handled. They also do address resolution, so the translation of symbolic addresses like actor references to physical references with ports and IP addresses. So sending and receiving entities do not actually need to maintain ports and addresses themselves. And they do data transmission, so the routing either one-to-one or one-to-many. So you can also do broadcasting via message queues if you want a certain message to be delivered to all subscribers of a certain queue. Usually they also manage the serialization and deserialization of messages. So you just take your domain object and send it to a message queue, usually by just specifying how you would like to have your messages serialized and deserialized, and then the actual serialization and deserialization will be done by the message queuing middleware itself. Also there, this is the same as we have done it in Akka. Right. Now to the transmission a little bit more. A message queue lives in some queue manager. So we talked about the queue manager before. This is the queue manager, the active component, the thread that maintains the send queue, or sometimes even the set of threads that manage the queues. And what we usually have is that a queue lives primarily in a certain queue manager. So this is where we eventually place our messages. But if a sender wants to send something from a different process, then its local queue manager will usually provide a temporary send queue. This is essentially the send buffer, also in Akka, where we can take our message and serialize the objects in. But we don't work with this directly. We don't see it. It's just used by the queue manager to bring our data over to the target queue. And then the message is stored in the target queue until the application fetches the data from this queue. Right. So, well, here the queue actually lives in the same process as the receiving thread. This is kind of also the the akka setup, but it can also be the other way around in other queue managers. Here in the we can even have the target queue within the same process of the sender, and the receiver connects to this queue manager's queue and fetches objects as messages over. So that's also possible. But like I said, so this would be the akka setup. Right, applications can read only local queues, and that's why we have this temporary transparent representation here. To read remote queues, the queue manager creates a local queue and then marshals the data over. Each pair of communicating processes contains usually exactly one transport level connection. So it does make sense, even if there are multiple queues here, the queue managers will create only one, in this case, for instance, TCP connection, and will send all the objects or stream all the objects over this one connection. Yeah, a process maintains usually exactly one send queue for each connection. So that all of them write to the same send queue, but on the target side, it is then put into the right target queues where the message should actually be sent to. Right, and next we need some routing table, so an address lookup database that stores a mapping of logical queue pointers to physical addresses, so ports and IP addresses. And this information is usually replicated on all queue managers. So this is like a shared, fully replicated database. Uses the technology that we learned about for full replication and keeping all the address lookup tables synchronized, so that every application can send stuff to every queue in the system. Okay, so this is the basic information that we need. Now the difference here is that we try to decouple the sender and the receiver by introducing a router process. The router process has the responsibility of receiving messages that cannot be sent directly to the receiving application, and then it forwards the message as needed. So there are queue managers that forward messages addressed to non-local message queues and are needed if the address lookup database is incomplete or network topologies are complex so that messages cannot be sent directly to the target queues. Right, so here the router is also another part of our application that doesn't receive the data and processes it, but just forwards it to the destination. But we usually use this only as an intermediate step to externalize the queue manager even further. So this is here a setup where we can actually do some persistent communication. We have now the sender and receiver set up as we have seen before, but we put the middleware mostly into its own set of processes. So in this setup, it's actually the middleware that stores the main message queues. So that the processes can read and write message queues fully independently from each other. Now we cannot only take the threads off and online, we can even take the entire sender and receiver processes off and online, because the data is actually not managed within these processes, but in processes from the middleware. There is no application code in these middleware processes, so they really act only as here as our routing tiers, so they do have the full replicated address lookup database, the sender and receiver applications, they do not need to know which senders and receivers there are. They just need to connect to the middleware. So they only need one IP address essentially and one port, namely the one of the middleware process here, to basically read and write message queues that are stored within. Right, they still have their temporary queues and buffers so that we can send the data over. And what we see here, even if there's a routing tier, they often use a send and receive queue or send and receive buffers in order to decouple the sending and receiving processes. And what they can even do is in the process, when they forward a message, they can even add a little bit of logic to it. So by moving the message from receive to send buffer, they can do a little bit of message translation if they know what kind of messages are being sent around. Right, and now we do it even more extreme by removing the queues from the sender and receiver altogether. So if queues are not stored in sender and receive applications, we can try to shrink the part of the middleware that is actually active inside of the sender and receiver application to an even tinier fraction. They do need some form of interface in order to talk to our middleware, but this can be done very small. And it can even be done, like in this example, with a different communication paradigm. So in this setup, this was end-to-end still message passing based. But in this setup, we switched to a different communication pattern, which is in this example, remote procedure calling. So instead of sending a message, they can actually take the message and then call a function in the message queuing or in the message queue manager on the middleware process and place the message with a remote procedure call directly into the message or into the send buffer. So this is something that the implementation of the middleware can decide. So the middleware can decide how the part of the middleware in the application, which is the part that you would import as a library to your application code, and then just call a few library functions, put, poll, subscribe, whatever the middleware system provides to you. And then the middleware decides how it wants to send over the message and what strategy it wants to use. And here it just decided not to use message passing directly, but a remote procedure call. Right, how these stub and skeletons work is something that we will later discuss when we talk about remote procedure calls. Just be aware that this is something that you can combine into the system. Right, the rest is still the same. There are the queues that are stored in some message message queuing middleware process, and yeah, senders and receivers can freely connect to it. Okay, so what else can the message broker do for us? So the distributed system usually consists of more than 2 nodes. Assume we want to integrate different potentially heterogeneous systems into a single coherent distributed information system, then in general, each system can speak its own protocols and message formats. And due to the complexity and abstractions made by the middleware layers, it is often not possible to let systems agree on a common protocol. So even if they use the same system, even if they see the same queues, they might still decide stuff differently. For instance, how their messages should be serialized. So in order to standardize this, in the message broker, we can do different things. And well, one thing we can do is to use wrappers, and the other one is to use the message broker itself. So in the case of wrappers, we can basically provide the logic of translating an object from one technology to another as a wrapper. And then process needs to know what kind of other process it is talking to, and then just use the according wrapper. So if there is peer-to-peer communication between all the attributes via their own channels, all systems need to use individual wrappers. And this, well, requires a lot of wrappers if your system is fully heterogeneous. And yeah, it works well for homogeneous systems, like ACA systems where everything is in the same technology. Then, well, there is only one type of wrapper that you need to implement, and then everyone can communicate with everyone else in a peer-to-peer fashion. But if they are different technologies, then you need quite a bunch of wrappers, and you are even not completely isolated because you have to know which wrappers need to be used. And the message broker can alleviate this, by providing a centralized communication hub and adding message translation features inside this hub. So there we only require a linear number of wrappers. So we need a wrapper for every specific system, but not a wrapper for the translation of every system to every other type of system. So we basically can talk to every type of system in a generalized format or in their format, and then we do the translation inside the message broker. This is a little slower than peer-to-peer communication because we have this central infrastructure. There's always one intermediate hop, but this hop can do the translation. And this brings us to a full-fledged message broker. So the message broker is an application level gateway on top of a message queuing system that routes and potentially also translates messages. So the part here in the middle where we had our queues, the queues live inside of queue managers, and the queue manager form the message queuing system. Is now accompanied by an extra logic, which we call the message broker. And the message broker, together with the message queuing system, forms then our message-oriented middleware. Right, so not every message queuing system is also a message broker. With a message broker, we have kind of an extension that can do a little more than just a stupid message queuing system. So yeah, a message broker can add additional capabilities on top of the message queuing systems, often via plugins or rules. And the tasks that it adds are message transformation and re-encoding strategies, replication of queues, partitioning of queues, like a distributed database. So we see this here. There are different brokers, and the broker, they make sure that this primary partition or this primary message queue is also replicated to this other broker. So there's a copy of the message queue that can take over if that part here dies. And this is not in the task of our queue manager. The queue manager is just for sending messages around, making everything reliable, identifying queues, managing our subscribers, targets, and maybe also the senders. That's the task of the queuing manager, and the message broker now adds all these extra features where queues are replicated or partitioned like in a database. Also, sender and receiver group management can be done here. This is something that we will see later on. And the batch processing. So it's the message broker that can say, okay, let's wait with the sending a little bit. We don't forward the messages right away. We wait until a certain number of messages have accumulated, and then we give it free and send it over. And this is when we now switch to something like Kafka, which does all of this. It's set up like this here. So we again have our application code. This is what we write. We imported some interface, and behind that interface is our message queuing system. In this case, it's actually also messaging based. We have seen before this can also use a different implementation, but here we are message based, and when we send something to some queue, then it is being sent to our broker process. Right. If we work with a broker, then we usually even assume that all the broker processes run on their own set of nodes, so that we have a reliable infrastructure with all the replication, and if something dies, other parts can take over. Inside the broker, we have the broker application. The broker application is something that we can, let me quickly finish this here and then we move on. The broker application is actually something that we can configure. That's also why it's gray here. There are certain plugins and rules that we can put in place such that the messages that we send here are translated accordingly. I already hinted this in the previous slide that this is something that is possible. So if we receive something, instead of copying it directly into the target queue, we do some translation of the messages into a different standardized format, or we can apply certain transformation rules that store the messages in the real target queue. And well, we have all the routing information in this middle tier that allow us to route here between different parts in our application. And also, if this is an active message broker, we can even route the messages to our receiving applications. Right, and in the receiving applications, we need to be able to receive messages and then provide them to the receiving applications. So this is, again, something that we actively need to program. Right. Here the message broker is shown as just one process, but as I said, these are usually multiple processes for reliability, for increased efficiency. We have seen this here also, because we have queues on different nodes, we can write to these queues in parallel and do this highly efficiently. All right, let me quickly check how many slides we have and where we can do a good cut. Okay, that's not something I can do in 5 minutes. But yeah, let me do the last 2 slides and then recap everything with RabbitMQ next time. So yeah, many, not all, and also not Kafka are subscription-based. So yeah, a subscription-based message broker means that they have an active component that allows reader processes to subscribe to message queues and then allow the message broker to deliver these messages actively to the processes once new messages have been arrived or have been written to the queues. So the queue manager of the message broker maintains all message queues, and any process can potentially access all the queues of the broker, and queues may be used in a many-to-many communication. So many-to-many means that, of course, multiple processes can write to a queue, and multiple processes can read or consume a queue in this model. Publish, subscribe is a message queuing communication pattern where senders called the publishers address their messages to specific queues, which often represent topics or categories, like a queue for all our offers, a queue for products, a queue for logged in users of our system, and then we have receivers that subscribe to these queues, and well, they can subscribe to one or even multiple queues. If there are messages, then these are delivered to them, and in this subscription, they register a callback function that tells the message broker how the delivery should look like. General message delivery, so the process can create named message queues, then others or itself can subscribe to existing message queues. It can send messages to a queue, and well, subscribing means that if there are messages, that it gets them if they arrive. The message broker promises that the sent messages are delivered to some or all subscribers. Also here we can usually configure the message queues if a message is a one-to-one delivery, something that is written is only sent to one destination, then it is removed from the queue. Or we can say that it should be delivered to all subscribers of that message queue at the time that this message has been sent to the queue. And then it will stick around in the queue for as long as it takes to send it to all the subscribers. Some popular message brokers are some commercial ones here. And we will have a quick look at RabbitMQ, which is a subscriber-based message broker. And later we will then have a look at Kafka, which is, a passive message broker from the other side, so that we basically get to know the two extremes of how a message broker can look like. Right, and that's our topic to restart the discussion next week. Next week we talk then about RabbitMQ, and I guess it will take us a little while until we talk about Kafka, but this technology is also coming. Yeah, thank you. Let me quickly check if there are any questions. No questions in the chat. Question from here. Awesome. Okay, so then, see you next week. Then I hope, I was super slow today. Then I hope we finish that chapter next week. And until then, have a productive week. Bye-bye.